Okay, so let's continue our discussion on Bayes' theorem. This is a special case when we have a situation like this, right? So here, suppose E and F are events from a sample space S, such that probability of E is not zero and probability of F is not zero. And in addition, now if you think about the Bayes' theorem and the way it's stated, is that probability of F given E is this entire expression up there, and F and probability of F, right? Over the total probability of E. Now, in certain situations, and just like going back to the visual that we saw when we were discussing the law of total probability, sometimes it might happen that there is some sort of, like, let's say this is E, and then there is an exact, and I'm not saying that this is an exact half and half, but there are just like two overlaps, right? So it's either F1 or F2, or a better way to say is like F and F bar. So essentially F plus F bar is this entire sample space, right? So for example, in cases like when we're talking about diseases, right? Somebody has the disease, or somebody, or the person, like a person has the disease or the person does not have it, right? In situations like these, we have just like two possibilities or two terms to break this down, which is what this expression is stating, right? So the probability of E can be written as probability of E given F times the probability of F plus probability of E given not F, right, times the probability of not F. Let's look at an example. Okay, suppose that one person in 100,000 has a very rare disease, and there is a test for the disease that gives a positive result 99% of the time when given to someone with the disease, right? And a negative result 99.5% of the time when given to someone without the disease, right? Okay, so we are interested in the probability that a person who tests positive has the disease. Let me just write down the events the way we've been doing earlier. So E is the event that the person tests positive, right? And F is the event that the person has the disease, right? So there is a test and either the person has the disease or the person does not have the disease, which is F bar, does not have, right? Does not have. There are just like two possibilities. Okay, so we are interested in who tested positive. I think we are interested in the probability that a person who tests positive has the disease. Yeah, so F given A. So given that the person tested positive, right? I was writing it the other way, but it's actually probability of F given E, right? So this is what we have to find out. Okay, so again, Bayes' theorem, right? Can we find the probability of F? Well, actually, it's given 1 out of 100,000, right? 2, 3, that's like really small. 0, 0, 0, 1, 2, 3, 4, 1, right? Okay, so again, we can easily find out the probability of F bar, which is 1 minus, the total probability has to be 1, so 1 minus the probability of F, which is 0.99999, right? Now, what is the probability of E given F? This is 0.99. This is already there, right? And what about the probability of, because we need all these terms if we think about the expression that we just wrote in the previous slide, right? So what is the probability of E given F bar? How can we find that? Now this is again easy to find because how many tested negative when it was given to someone without the disease? All you have to do is 1 minus 0.995, right? Which is 0.005, right? Now we have all the parts that we need to plug into this equation here, right? And that's what we'll do. Okay, so there isn't much space. However, I'll try to write it here like a little smaller. Let me make a box here maybe, because again, we're interested in probability of F given E, right? And then I'm plugging all the values into the formula earlier. Now I have all the values, 0.99 times 0.00001 over, again, 0.99 times the same thing, 0.00001 plus 0.005 times 0.99999, right? Which comes out equal to, let me do the calculation, 0.002. Okay, so that's one example demonstrating what we meant by this particular formula, right? You just have two possibilities of the event F. So coming to why Bayesian probability is useful, you can see with this example sometimes a disease test, for example, in this case, wasn't extremely useful. And this can help us show the counterintuitive results, right? So for example, the disease test that we just used was not very useful because looking at the probability that a person who tested positive has the disease is like really, really low, right? So Bayesian probability helps us put probability values on unknowns, right? We can make inferences regarding some uncertain statements. And also, Bayes' theorem actually converts the results from a given test into the real probability of the event. And this is, I would say, the most important part of Bayesian probability. Okay, let's look at another problem and another strategy to solve these kind of problems. And that strategy is to put all the information that you know into a table that's shown here, right? Again, this is a similar example, like quite similar to the one that we just saw. So 1% of women have cancer. So, and this is the information that I'm inferring from the question. So this wasn't part of the question, right? And so therefore 99% do not have, right? Again, 80% of the tests available detect cancer when it is there. So when cancer is there. And so 20% miss it, right? And it's given 9.6% of tests detect cancer when it's not there. So like 100 minus 9.6, which is 90.4%, correctly return a negative result. Now I'm interested in the probability to really have cancer if we get a positive result. So I'm interested in probability of getting cancer given that I tested positive. Right? So even before I go in and get these values and plug into the formula that we saw earlier, it's better to put everything in a table because it's easier to read from this. Now this is one known strategy of solving such problems. So for example, there is this possibility of people having cancer, that's 1%, that's given to me. So obviously 99% don't have it, right? And then on the left hand side, I'm talking about the test, right? So I'm talking about the test here, I'm talking about the disease here. So people who have cancer, 80% of them test positive, 20% test negative. People who don't have cancer, 9.6% positive, 90.4 negative. And now, like reading out values to get what I need, which is probability of cancer given positive, is actually probability of cancer. Or I should have written like, let me write it the other way. Like this term should have come first as per the formula, right? But I'm writing it positive cancer, which is the same thing as writing probability of positive given cancer over the probability of positive. Now, as you can see, it's easier to plug in values here rather than getting each term like we did in the previous example, right? Probability of getting cancer, I know it's 1%, right? Probability of testing positive given cancer, testing positive given cancer, 80%, right? Probability of testing positive. So this entire line, right? This entire row. So just add 0.80 plus 0.96, 0.096, right? So that's how you'll get this. Okay, so this table method actually makes our life easier because we can just like read off values from there and plug into our formula for Bayes' theorem. Okay. One final example, Bayesian spam filters, and this is actually used in a lot of spam filter applications. So suppose that we find a word Rolex that occurs in 250 of some 2000 messages known to be spam, and in 5 of like 1000 messages not to be spam. So it's similar to that disease test if you think about it. Now estimate the probability that an incoming message containing the word Rolex is spam, assuming that it's equally likely that an incoming message is a spam or not spam, right? So there are two things that are possible, disease or no disease. If our threshold for rejecting a message as spam is 0.9, will we reject such message? So essentially we're looking at like what probability we'll get, and based on that, if it's more than 0.9, I'll reject it, otherwise I'll not, right? So let me just state what I'm looking at. My event S is message spam, and E contains Rolex, right? Okay. So what exactly am I interested in? I'm interested in probability of S given E, right? And I can directly use the formula that we stated earlier, which is, and I wouldn't like go and write it again, but it's going to be probability of, or let me quickly do that so that we don't forget. There's S, and then this is going to be the total probability of E, which we can do by saying probability of E given S times probability of S plus probability of E given not S times probability of not S, right? Okay, so what we have to figure out is probability of S, probability of E given S, probability of E given not S, and probability of S. Yeah, I already said that, right? Okay, so let's quickly find out each of the values in that equation and then plug into the equation, right? So I know that probability of S is going to be the probability of not S. Equally likely, it's already there in the problem. So that's 1 over 2. Now, the probability of S, probability of E given S, right? E is the Rolex word that's there, given that it's a spam, right? Again, I have the frequency values. I'm just plugging in those to get this part, which is 1 over 8, which is actually 0.125 if I remember correctly. Okay, what is the probability of E getting a Rolex and a non-spam? It's going to be 5 over 1000, again given to us, and that's 0.005. So the probability of E given, okay, so that's all we need, I think. So now the probability of S given E will be 0.125 over 0.125 plus 0.005. Why? Because the other total probability is 1 over 2 for all of them, like S and S bar, so they all get cancelled, right? So this, and we have to compute the entire thing because we really need the actual value to decide whether we need to reject it or not. And now this is definitely greater than 0.9, so we reject as spam, right? Okay, so with this I finish this video on Bayes' theorem.